Hello. Today we're going to be talking in this video about common logarithms. And I have some notes that are going to be important written up in front of you. So a common logarithm is just a logarithm without a base. And you can kind of see that in this example right here in log of 100. So if you are looking at a logarithm like that, it just means the base is actually 10. And that is something that's going to be important for when we're evaluating certain things or when you might be using logarithms for certain uses. And we're going to talk about those uses in our next video, part of the video. So we'll come back to that a little bit. But right now, let's kind of talk about how you might evaluate common logarithms. So when you are thinking about how this would look, you would basically have a logarithm like if you wrote it out as log of 10. Well, that would be the same thing as having something be equal to log base 10 of 10. And when we're doing our evaluating logarithms, we just want to think about how long it would take 10 to multiply it by itself to reach 10, its input. So we only need 1. So this would mean that 10, we know 10 to the first power is equal to 10. So that means the log of 10 is going to be equal to 1. Another example of this would be something like if we have log of 1,000, we know that that is the same thing as log base 10 of 1,000. And from there, all we need to think about is 10 to what power is equal to 1,000? Well, we need 10 times 10 times 10 to make 1,000. And that means that log of base 10 of 1,000 is going to be equal to 3. Let's rewrite that real quick. And we know that's going to be equal to 3. 3. And that's really all you need to know about common logarithms. Just remember that whenever you see just a logarithm like the one I've drawn right here, you need to remember that the base is actually a 10, and you can just think of that 10 being there and evaluate that logarithm as if it was there the whole time. We are now looking at how to do common logarithms on the calculator, and it is very easy. We are looking to evaluate things like log of 100. We know that log of 100 would just mean log base 10 of 100. And you might remember that from what I mentioned earlier. So if we're thinking about this logarithm right here, well, we would think of that instead as log of base 10 of 100. Well, we know that would equal 2. 10 to the second power equals 100. So if we go over to my calculator, if we find the log button, which you'll find next to the left of the 7 button, if we just click on log, you'll see that there's no base that comes up. And if we type in 100 and close parentheses, it gives us the answer that we just got. And we can remember that this common logarithm is going to be base 10 because if you look at the logarithm button on the calculator, if I push second and then log, I'll see, well, it's giving me a 10 as a base. for this exponential. So I could do 10 to the second power, and it obviously equals 100. That should be a reminder that common logarithms, when there is no base at all on the calculator, you can use a 10 as the base. And that is all you need to know about using common logarithms on the calculator. We will now look at a quick example of applying the common logarithm and logarithms in general to the real world. Let's read through this really quick. So it says many measurements of physical phenomena have a wide range of values that are reported in measurements by logarithms, where things are increasing exponentially on one hand and they're increasing by just one number on the other. So when you think about exponential growth, usually your x-axis is a certain amount of time, and that time is going forward like days, 0, 1, 2, 3 days. And then an amount is going up on your y-axis exponentially, very quickly. That is what you kind of see in the bottom when you're multiplying by 30 a number of times, and you kind of recognize that's exponential equation or exponential functions. Now, for logarithms, they are the inverse, and so that means they are the opposite. That your x-axis is energy increasing at a very rapid rate, but the y-axis increasing at a much slower rate. And in this case, the y-axis is going to be the magnitude of earthquake that you measure on the what is called the Richter scale. And the energy released is what is released from the earthquake. So you can see how the energy would increase very rapidly on your x-axis by multiplying by 30 a certain number of times above and beyond what the normal energy released in the earth on any given day is when there is not an earthquake. So let's do a quick example problem together of this being used. So in this problem, you have a earthquake that is happening in 2004 with a magnitude of 9.3 on the Richter scale. And we have in 2004 an earthquake of magnitude 9.3 on the Richter scale hit off the northwest coast of Sumatra. And we can measure that earthquake as well as another one in 2005, in March of 2005, using the formula presented in this paragraph. The log of intensity of the first earthquake divided by the intensity of the second earthquake, and that's like energy released in general, and that is equal to the difference in their magnitudes. And so we could do this with logarithm, but we're going to compare these two earthquakes using one logarithm formula. So let's start by writing out our logarithm thing here. So we have a logarithm, and we have a division of two intensities. So I have I1 and I2. I1 and I2, and that is equal to the difference in the magnitudes. And so our magnitudes for the two earthquakes was the first one was a 9.3, and our second was a 8.7. So we have 9.3 minus 8.7. So from there, well, we know that we have to put in our 10 because this is a common logarithm. So our action here that we're going to be doing is we're going to be subtracting these two numbers and then using 10 to that difference is going to be equal to this fraction. So let's do that now. So we have this down here would be equal to 6. So 10, we would have 10 to the power of 0.6 would then be equal to this fraction. So we have I1 over I2 I2 is equal to 10 to the power of 0.6. Now that ends up 10 to the 0.6 equals 3.98. So that means that that fraction of I1 over I2 is going to be equal to 3.98. So if you have a fraction and you don't know either thing about that fraction, I1 or I2, but we know that if you divide the top one by the bottom one, the answer is 3.98. That tells us two things. The first thing would be the top of the fraction is obviously bigger. When you do division, if you get a bigger number than 1, the top is definitely bigger. We can also say that the intensity of the first one is 3.98, or about 4 times more than the intensity of the second earthquake. So if we are comparing these together, we would basically see that the intensity of a 9.3 compared to an 8.7, which is about a half number up on the Richter scale, would be 4 times more energy released. So you can see how that can go up very quickly. And that concludes our discussion today on common logarithms, how you use them on the calculator, and how you might apply them to the real world.